Thank you too for your introduction. I hope you can see my slide and hear me clearly. So my name, thanks. My name is Nico Schütte. I'm doing my PhD at Leibniz University in Hanover. And today I'm going to talk about resonance analysis in electrical power transmission grids. As we are new to Interessenverband Netzimpedance, I would like first to introduce our institute. It's Institute of Electric Power Systems, and it consists of 3 different sections. Me and my colleagues, Mr. Neufeld and Mr. Wingenfelder, also attending today, are working at Electric Power Engineering section, but we're also associated with Electrical Energy Storage Systems section and High Voltage Technology section. In total, we're 14 researchers working on different different research topics. I brought this picture to show our main research topics. The most is about modeling and simulation. For example, we're doing optimization, control strategies, market simulations, and also fault calculations. And my part is on harmonics and network resonance analysis, and I'm focusing on EHV and high voltage level. So about my agenda today, I would like to give a short motivation why we're doing research on resonances. And then I would like to introduce the methods we use to analyze these resonances in transmission grids, and to give an overview about previous studies. And I will close with a short outlook. So what drives our research is that we expect resonances in transmission grid are changing. There are several aspects. The main 2 of them consist in the introduction of underground cables to EHV transmission grid, which is more like a political thing, as there's a lack of residents' approval towards overhead wiring. And it's interesting from technical view because these underground cables have much more capacitive behavior compared to overhead lines. Also interesting is that we have a number of new devices, power electronic devices in EHV and HV level, which is a gain of nonlinearities and harmonic current injections. So talking about harmonic current injections, I would like to focus on the normative framework I'm working within. So mainly there are 2 guidelines I'm currently working with. The one is IEC Technical Rule 61036, which provides indicative planning levels for harmonic distortion in transmission grids. And it also provides the allocation method to assign maximum harmonic voltage and also current limits. And this is based on an optimal utilization of these planning levels provided in this guideline. The specifications are made up to 5th harmonic order. And that's the range where we're currently working when we're doing resonance analysis in transmission grid. The other guideline is the German one, introduced by VDE with number 4130 for extra high voltage level, and the same for high voltage level, which is 4120. And it defines binding basic rules for German network customers. This means there are something like a flexibility for users to use this rule, but it's mandatory to respect these basic rules. It also provides the allocation rule for maximum harmonic current limits. And these specifications are made up to 40th harmonic order. So as I said, we're focusing on a frequency range up to 2 or 2.5 kilohertz. So what are our research aims? As I already said, we're interested in allocation of harmonic current limits to connectees in the high voltage and extra high voltage level. And therefore, And also for other aspects, we're interested in analysis of resonance behavior of these transmission grids, especially on the effects of grid expansion and the transformation of the transmission grid. As a basis for this analysis, we need to determine and to improve modeling guidelines and also to improve analysis methods. And in the following slides, I would like to give a short overview about our resonance analysis methods we're using, which are 4 of them: the frequency scan analysis, resonance mode analysis, participation factors, and the sensitivity analysis. Starting with frequency scan analysis, that's the most simple method of investigation, and it is mainly the examination of diagonal elements of the nodal impedance matrix, or also possible to do it with admittance matrix. And using it for such an exemplary grid configuration consisting of 3 nodes, 2 lines, 2 loads, and a generator, it's possible to get different curves and to identify potential resonances. There are probably 3 of them, which can be detected as the first one, the second one, and the third one. But it's observable that these resonances overlap mutually. So the problem with this method is that the characteristic values of these resonances depend on the node they are observed from. So facing this, I will show another analysis method, which is the resonance mode analysis. And we use this to clearly separate the calculation of parallel and series resonances. Mainly is some kind of decoupling of the system via modal components. So we transform the system formulation in a modal system formulation. And what we get is like single resonance circuits, which are explicitly separated, and it's easier to determine the resonance frequencies and the modal impedances. So this is the same grid configuration, and as you can see, now it's clearly observable the first, the second, and the third resonance frequency. One of the disadvantages of this method is that these modal impedances are not the same as the network impedances, as we're now in modal system formulation. And the following method, which is the participation factors, describes such thing like a link between this modal formulation and the nodal formulation. On the basis of this participation factors, it's possible to find the nodes that are related to a single mode. The determination can be done via eigenvectors and eigenvalues. And these values do already exist, as they are already needed to do this decoupling for resonant mode analysis. So when applicating for this first mode with a resonant frequency of 290 Hertz, it's possible to see the participation of node number 3 to be the node with the strongest excitation that can be expected there. But unfortunately, the informative value is limited, as we can only see the participation of single nodes, but it's not possible to find the influence of single components on this resonance. So this brings me to the sensitivity analysis, which is used to determine the influence of individual components in the network. And sensitivity means that it is used to describe the shift of resonances when component alpha is varied. So it can be, I can differentiate between the variation of modal impedance magnitude and also the variation of resonance frequency. For the exemplary arrangement I was showing on the first slide, I can do such a frequency sensitivity index for this first mode, which was with a resonant frequency of 290 Hertz. And it's possible to rank the elements that are most sensitive to this mode. So as you can see, the element which is the susceptance at node number 3 will be the element which which is most participating at this mode. On this image, you can see that this kind of rank, which was determined, can be seen when the elements are changed, just to see if the method fits. And the orange curve shows that when every of these elements is changed to a similar extent, the frequency decreases the most for the orange curve, which is element the susceptance at node 3. So far that's about our analysis methods we are mainly using. And in the second part of the presentation, I would like to give an overview about the previous study we conducted. So the first I would like to talk about is was dealing with the effects of grid expansion with HVAC cable corridors. It was a study section of the German EHV transmission grid, it's Northwest Germany. And it was including 3 underground cable pilot projects, which can be seen here with gray colored. All these cable pilot projects were studied with hybrid lines, which means these sections consist of overhead lines and underground cables in different ranges. So as I said, we expected the resonance behavior to change as the cables have higher capacitance per length, and also because these lines are designed as a 2 system. Coming to the main outcomes of this study, we saw that there's with an increase of cable shares, which you can see here in the title of the system, it's constantly increasing. There is a mainly decrease of resonance frequencies for a lot of modes. So you can see the resonance frequency mainly decrease and also the magnitudes decrease. But many modes have different impact, like not every mode is sensitive to this cable, which was varied. So it depended much on the harmonics themselves and also on the nodes where they were observed. So this is another picture showing the degree of cable penetration for the same study. And you can see the maximum or the resonant peak changing over harmonic orders. And as I said, some modes are sensitive and fastly changing and decreasing. Others are not that sensitive. Yeah, just to give an overview, there are many questions left to focus on. Yeah. Another study we wrote out was also about the variation of cable share in transmission grids, which was a probabilistic analysis where we did probabilistic calculation of harmonic voltages. So you can see here, we had a look for exemplarily a fifth harmonic order and wanted to see for harmonic voltage level of IEC guideline, where when the we wanted to see how probably this limit will be accessed when the modal impedance of a single resonance will meet this fifth harmonic order. So what we used was like future grid forecast. We conducted with today's time series measurements and used it within probability density functions. Another and the newest study we conducted is about allocation of harmonic emission limits, as grid operators are confronted with the selection of suitable allocation methods to assign these harmonic emission limits. So what we focused on was a comparison between VDE guideline and IEC technical rule. And what we saw is that with some modification, they can brought to broad conformity, as you can see here. And what we also saw is that it's necessary to investigate the network impedance exactly, because for this resonance condition, the harmonic emission current limits are very limited. So that's really important to determine these network impedances correctly. And that's the point to the need to investigate the network impedance correctly in extra high voltage level. I would come to the upcoming research issues and the outlook. What we're currently focusing on is the evaluation of study area selection to stake out topological model boundaries, and to also investigate how neighboring networks from different countries or other regions can be handled, maybe to adopt different modeling deepnesses for neighboring networks. Also, we investigate modeling issues and improvements, which basically concentrates on the modeling of downstream networks, like high voltage and middle voltage network, and also on loads. Also, we concentrate on the modeling of power electronic devices that are new to extra high voltage level, like HVDC converter station or FECs. And in general, we concentrate on the enhancement of appropriate analysis instruments and methods. So that's about my field where I'm focusing on. We also have colleagues working on harmonic stability, which is Mr. Neufeld also attending, and Mr. Wingenfelder, who's also working on a little on harmonics in low voltage regarding e-mobility. So that's it. Thank you for your attention, and I'm open for your question. Thank you.